The following program was produced by an independent community producer. The opinions expressed do not necessarily reflect those of the QATV staff or board of directors. QATV, in compliance with FCC regulations, is prohibited from exercising control over the content of independent, member-produced public access programming.
Hi, my name is Peter Gleba. My background is in geology. In the course of teaching physical science, I became interested in astronomy. This program is an image overview of astronomy. It deals with the history of the science, the discoveries made now and in the past, and astronomy's theoretical underpinnings. The title of the program refers to the nature of the evolution of humanity towards its destiny in and out of the universe. As any child, we will leave our nursery planet Earth. And now for the first slide. This is a diagram of the expansion of the universe called the Big Bang. The shape of the universe is not a tuba, this is just a diagram, and the expansion began 3.7 billion years ago. And it occurred out of a quantum fluctuation out of the nothingness. And it came from a singularity that was smaller than a trillionth of a proton, much smaller than an atom. And you can see the white glow of inflation and then the afterglow pattern 400,000 years after the beginning of the universe. To the far right, you see the satellite which mapped that pattern. We entered the dark ages when there wasn't any light, and the first stars began forming about 400 million years ago, 400 million years after the beginning of the Big Bang. And there may be, other universes forming at the same time, before and after and forever. No one really knows. This is the pattern, the afterglow pattern. And the dark areas are the cooler areas, and the greenish, reddish areas are the slightly warm areas. The temperature of the universe is just above absolute zero. And if it weren't for these slight temperature fluctuations, the galaxies could not form. In 1965, two Bell telephone scientists, Wilson and Penzia, discovered this radiation that came from everywhere in the sky. And in fact, when we had the old-fashioned television, part of that snow you saw in between channels was was this radiation that you see here. Only 4% of the universe is visible to us. The rest is invisible. As you can see, 74% dark energy, and the other part is dark matter. We know the dark energy is out there because the expansion of the universe suddenly increased about 5 billion years ago, and it's thought to be due to this dark energy. And this dark matter is thought to exist because of its influence on the galaxies around us, including ours. Now, when the universe expands, we can use this raisin bread model. When you heat up raisin bread dough, it expands just as the universe. And in the center, where you see that raisin, there would be galaxies, say, 50 million light years away from us, and 100 light years away, 5 and 10 centimeters respectively. You can see that if the universe doubled its size, the distance of those two galaxies would increase proportionally, so that the raisin 5 centimeters away would be then 10 centimeters, and the one 10 centimeters away would be 20 centimeters. What this means is the galaxies further away from us are moving much more rapidly than those closer to us. And this is the person, Edwin Hubble, who discovered it. And in 1925, he discovered that there were galaxies outside of our own, which are a galaxy called the Milky Way galaxy. And in 1929, he announced that the galaxies further away from us are moving away faster than those closer to us. This is the instrument they used. This is the 100-inch Hooker telescope on Mount Wilson in California. The 100-inch refers to the diameter of the mirror in that telescope. And like astronomical advances have been due to a great deal due to advances in technology. This, of course, is the Hubble telescope, space telescope named after Edwin Hubble. And in the near future, there'll be another space telescope being sent up that has a mirror 4 times the diameter of the Hubble. So given the wonderful images the Hubble telescope has been sending back to us, the next one will be even more incredible. Now you may wonder, how do physicists know what the makeup of the universe was way back then? Well, what they do is they smash particles. And this is the CERN collider that's on the border between Switzerland and France. And what happens is they send particles, protons, down that track and to smash into other particles. And this is the tube down which those particles are being sent. They're guided by magnets, and this is the result of the smash. The particles get smashed apart, and the particles get examined, and we can tell down to a finer size what the particles of the universe is made of. And they had some teething problems, but in December of this year, 2009, they'll go to half power, and hopefully by next year they'll go to full power, and we'll get even deeper into the mysteries of the universe. Right now, physicists can go back almost to the instant of the Big Bang. To go to the moment of the Big Bang, would have to build a collider that's trillions of miles in extent. This is an artist's representation of the universe. And you can see the section there showing 1 billion, and the universe is nearly 14 billion years. And we're near the Virgo supercluster. And again, we're not in the center of the universe. We could be anywhere. This is just part of the diagram. But you'll notice that the galaxies that you see are clumped. And what's happening is the galaxies are being drawn together and into these clumps, and with these enormous voids in between galaxies. And this is a deep space view taken by the Hubble telescope. What the Hubble did was to look at a small section of the universe for days, taking a long photograph. And each of those little lights that you see is a galaxy. There are estimated to be 100 billion galaxies in the universe. And in the center of each galaxy is a black hole, which I'll describe later. And surrounding each galaxy is dark matter. Now we're getting closer to our galaxy. In the center, the Virgo cluster. And you can see that the clusters of galaxies around us look like snowballs. And even closer, again, we're in the center of this diagram, and you can see there are a great number of galaxies around us down to the lower right. This is the Whirlpool galaxy, maybe one of the most spectacular, beautiful galaxies of all. And our galaxy looks similar to this one with spiral arms. And again, in the center, there's a black hole, which I'll describe later on. Now, given the enormous size of the universe, you would think that galaxies would be able to miss each other. Not so. Galaxies collide and they come by, and that is going to be our eventual destiny in a while. This is 2 galaxies that are in collision, and this is called the antenna galaxies because they have a long tail, not shown in this photograph, but as you can see, they're interacting, again, in a beautiful, spectacular manner. This is, again, one of the most beautiful galaxies called the Sombrero Galaxy because of its resemblance to a sombrero. But not all galaxies are as perfect as that one. This is a warp galaxy, and the reason why it's warped, it's thought because it was in a recent collision. And after millions of years, it'll settle down and probably look like the Sombrero Galaxy. This is an artist's diagram representation of our galaxy, the Milky Way galaxy. We cannot go outside our galaxy and take photographs, but this is what it would look like if we were able to do so. And this diagram shows the location of our sun. As you can see, we're well away from the center of the galaxy, which is just as well, because you can see there's a lot going on. There's a lot of radiation in the center. We want to be in a quiet neighborhood, away from all that trouble, and live a quiet life. This is the Andromeda Galaxy. As I mentioned, most galaxies are moving away from us, but the Andromeda Galaxy is only a bit more than 200 million light years away from us. And because it's so close, relatively close, it's being drawn toward us. Now, I should explain to you what a light year is. In the vacuum of space, light will travel at a rate of 186 miles plus per second. So you can take that amount of time in a year, the distance that light will travel, and that turns out to be almost 6 trillion miles. So the Andromeda Galaxy is around 13 million light years away from us. But nevertheless, it's coming, and in about 2.5 billion years it will arrive, and that galaxy and our galaxy will collide. And we'll see what happens then, if humanity is around then. This is, again, an artist's representation of the formation of our solar system. What happens is that a gas cloud called a nebula will collapse and concentrate in the center and form a star. And as you can see, the early sun would emit jets. But circling the sun, or a star, is a solar disk composed of rubble material, and it is whirling around. And this material coalesces, giving us our planets. And here we can see a solar system forming in another star. This is a star called Beta Pictoris, and you see that red-orange glow, which is the disk around this particular star. Astronomers have found other solar systems in the formation, being formed, and with organic molecules toward the center of the disk. And these organic molecules could very well give rise to life, as it did on this solar system. Now, this is the reason why the Milky Way is called the Milky Way. What you're looking is directly down the plane of the galaxy, and what you're seeing a cloud of stars. And this next image is the same image except shown in infrared. And unfortunately, you can't see the Milky Way unless you're away from urban areas, away from the light pollution. You want to be in a very dark part of the country where there are no lights destroying your night vision. Then you can see the Milky Way. And here we're looking at the center of our galaxy. And each of those little specks that you see is a star. Depending on the authority you talk to, there's either 100 billion or several hundred billion stars in our galaxy. So you can multiply 100 billion galaxies by hundreds of billions of stars in one galaxy, and you can get an idea of how many stars there are in the universe. This is our sun. And you can see there's a prominence in the upper right-hand corner. And the reason why it's glowing like that is because of thermonuclear reactions. What's happening is hydrogen gas is being fused into helium. And part of the hydrogen atom is converted into energy, giving us the light and heat that's emitted by our sun, which is a medium-sized star. Now, you may wonder how astronomers know what the chemical composition of stars are. Well, the secret is Fraunhofer lines, named after the scientist who discovered the fact those little black lines that you see, by examining the position of those lines, you can tell which elements are in a gas, and that's how they do it. And so for our next slide, this is the surface of the sun, and you'll see the prominences of gases being erupted out from the surface of the sun. This is, again, the surface of the sun, and these are the granules. Each of those granules, the yellow areas, are about 600 miles across, and those are the hot areas, and the gases come up to the surface, cool off, and sink down again, and those are the black areas that you see. And these are sunspots, and what happens is magnetic fields erupt out of the sun, and what you see here is a north and south pole of magnetic fields called sunspots, and they come in 11-year cycles, go across the face of the sun. And the reason is the sun is rotating just as the planets do. And it's out of these sunspots that the eruptions of gas occur. This is a solar eclipse, and that area that you see around the eclipse, the sun is being eclipsed by the moon, that's called the corona of the sun, and that's where the solar wind comes. The sun is emitting particles into space and is bombarding our planet as well as other planets. And down in the left-hand corner, you'll see the sun, and you see a protuberance. But luckily for us, you see these blue lines around the Earth. That's a magnetic field. The Earth generates a magnetic field, and those are lines of force. And luckily for us, as the particles bombard the Earth, the magnetic field is distorted but protects us from all the radiation from the sun. And what happens is the magnetic fields get concentrated both at the north and south poles, and the particles from the sun are concentrated at the north and south poles. At the north pole, it's called the aurora borealis, and in the south, it's called the aurora australis. What happens is the sun particles interact with the oxygen and nitrogen in our atmosphere, creating those colors. And if you look toward the bottom of the screen, you'll see a round circle. That's called the Mancougan crater. That many years ago, an asteroid hit northern Quebec, leaving this crater. And there are maybe about 100 known craters on the Earth. And this is a close-up in Alaska of the aurora borealis. It's really a beautiful sight, and of course, it's sitting still here, but when you see it alive in nature, this green color just pulsates across the sky. Now let's talk about some of the most famous astronomers. This is an early Greek astronomer called Ptolemy, and what he said is that the Earth is the center of the solar system and the sun goes around the Earth. And for hundreds of years, that was accepted view. Of course, it's not natural to see because the sun rises in the east, sets in the west, and it does seem that the sun goes around the Earth, but that's not the case. This is my fellow Polish countryman, Nikolai Copernicus, and his image is on a 1,000 zloty Polish banknote. And he proposed that the sun, not the Earth, was the center of the solar system. This was termed the heliocentric theory. And he published a book and established his theory. But it took a long time before his theory, the heliocentric theory, was accepted. Now, this is Galileo, and he can be considered one of the first, the father of modern science. The reason is because he conducted experiments. He did physics experiments, but particularly for astronomy, he built a telescope. He wasn't the first to build a telescope, but he was the first one to really use it to some effect. For example, he spotted Jupiter and 4 of its moons, which lent credence again to the fact that the Earth was circling the sun rather than the other way around. He saw Saturn, which he said had ears, but his telescope wasn't good enough to see what Saturn really was. Those ears are really rings around the Earth, around Saturn. And unfortunately, he also looked at the sun, saw sunspots, which eventually led to his blindness. Well, he believed in Copernican theory, and he wrote a book which didn't go over too well with the Catholic Church. And he was sent to the Inquisition, and he was forced to recant the Copernican theory, and he was sentenced to the rest of his life, 11 years of house arrest. And he slowly went blind because having looked at the sun. A couple of other famous astronomers. This is Tycho Brahe. Unfortunately, this image is somewhat distorted, but he was a Danish astronomer, and he made the most accurate observations ever done using eyes. The telescope hadn't been invented by the time he was doing astronomy, but his data was passed on to his assistant, Johannes Kepler. And he came up with the 3 laws of planetary motion, among which is that he said the planet orbits are not perfect circles, they're ellipses. Nearly perfect circles, but not perfect enough, and which makes a difference in the seasons, and it has an effect on our planet. And he also, one of his other laws was that the Earth and planets move faster as they approach the sun because of the sun's gravitational pull. And this is perhaps one of the most famous key scientists in history, Isaac Newton. In 1665, he was at Cambridge University, and the Black Plague hit London, and he went home and stayed at his mother's farm until the plague abated. And during that time, he came up with many of his ideas. And for example, he came up with calculus, came up with the laws of motion, came up with the law of gravity, which stated that the gravity increases with the size of the mass of an object, and also gravity decreases in strength according to the square of the distance between masses. So anyways, he kept this under his hat for many, many years until he was encouraged to publish his book called the Principia, and this led to the Newtonian view of the universe, the clockwork universe, where the movement of planets could be predicted. Now, jumping ahead to Albert Einstein, this is a picture of him as a young man in 1911. And he did his work in the early 1900s as a young man. And in 1905, he published the theory of special relativity. And in 1915, he published the general theory of relativity. And here he is as an older gentleman. He left Europe and came to Princeton, where he spent the last years of his life being a seer. And you can see that the genius just sparkling out of his eyes. That's such a huge number. It takes a very small amount of matter to create a great deal of energy. And our solar system is 4.6 billion years old, and it's going to go on for another 5 billion years. And the reason is because it doesn't take a great deal of matter to create a great deal of to create a great deal of energy. And this is one of the things that Einstein predicted in 1930, called the Einstein telescope. And what you're seeing here in the center is a galaxy, and around it is 4 images of the same thing, and a great distance behind that galaxy called a quasar. A quasar emits a great deal of energy, and that galaxy acts as a telescope, bringing those 4 images around it. And Einstein said that this was a theoretical interest, but no practical interest. But given their advances in technology, we're able to see huge distances into space. And there's a book called Einstein's Telescope that deals specifically with this. Now, one of Einstein's statements is that space-time acts like a rubber sheet. And Newton said that gravity is a force. What Einstein says is that planets bend space. And here you see the Earth bending space. And what happens is that objects fall toward bigger objects. And for example, our moon is falling toward Earth because Earth is bending space. But the moon doesn't collide with the Earth because it keeps rotating because of the centrifugal force that was given to it initially. And here you see on a bigger scale our solar system. And you see that the sun is bending space-time, and this is just a diagram. It's not to scale. And you can see the other planets rotating around the sun. And coming in the left-hand corner is a small comet, which will whip around the sun and go back out again. And comets are made out of basically snow and dirt, and eventually it'll evaporate. And those specks you see in the foreground are asteroids. Now, stars are being created in nebula. This is another Hubble Space Telescope. of called the Eagle Nebula, and these are pillars of clouds of gases, and each of these pillars, stars are being created and solar systems being created. And this is called the Horsehead Nebula for obvious reasons. And going forward to the Horsehead Nebula. Well, we'll go to the HR diagram. This is the Hertzsprung-Russell diagram. And stars are classified like people. You have old people, young people, small people, tall people, what have you. Stars are the same. Now, running through the center of this diagram is what's called the main sequence. And our sun is right in the center. It's a nice medium size. And down in the lower right-hand corner of that main sequence are the very small stars, and way up in the left-hand part of that main sequence are the much bigger stars. In the upper right-hand corner of the diagram are the huge giants, and way down in the lower left corner are very small stars called the white dwarfs, which I'll discuss in a bit. And this to give you an example of relative size of stars. Our sun is a star, and you see this is the Arcturus star, and you can see how big it is compared to our sun. Now, one of the most interesting stars is the Betelgeuse. And Betelgeuse is a huge red giant star, and apparently is expanding, and it may eventually blow, and eventually our star will resemble that in 5 billion years. And this is a star that has blown. It's formed what's called a planetary nebula because it's round, and this star has blown, and in the center you'll see a white dwarf. This is a ring nebula, and again in the center there's a white dwarf, and eventually again our sun is going to look like that. Our solar system will disappear, and we'll just have a cloud of gas being emitted out into space. This is a white dwarf, and this what eventually is what our sun is going to be. What happens is when a star runs out of fuel, when it starts running out of hydrogen, there's an inward pressure pulling the gas inward by gravity, but there's outward pressure due to the thermonuclear reactions. Well, once the hydrogen starts going down, the inward pressure starts taking over, and there's going to be a collapse inward, and this is the white dwarf. And when our sun gets down to carbon, it's going to blow. And what you see here is compressed carbon. It's interesting because eventually this white dwarf is going to cool off, and it could be that there are planets the size of the Earth out in space that are made of diamonds. Just an idea, but it's possible. This is a binary star, and this star hasn't exploded, but it may eventually explode and create what's called a neutron star, which I'll discuss. And this is called the Crab Nebula. This is a star that exploded many centuries ago, and in the center is a star called a neutron star. And this is an artist's diagram of it. Now, depending on the size of a star, it'll leave different cores behind. Up to a size of 1.4 sun masses, it'll leave behind a white dwarf, which, as I said, is compressed carbon. But if it's larger, it'll leave behind a neutron star. And this is an example of one. What happens is electrons get smushed into protons, creating neutrons. And this material is extremely dense. A teaspoon will weigh many, many tons. And a neutron star will be very active. And there's some that spin and give off emissions that are called pulsars. Now, as I said way in the beginning, at the start of the Big Bang, there were only 3 elements: hydrogen, helium, and some lithium. Well, when stars explode, they create the elements that we know, the natural elements and most probably the man-made elements. So that the elements that make us up, for example, carbon, oxygen, and trace amounts of iron, and everything you see around you was created in stars. So that in essence, except for the hydrogen, we are made out of stardust. And if it wasn't for the death of stars, we wouldn't exist. Now, when a star is very massive and it compresses, it goes beyond the white dwarf, it goes beyond a neutron star, and it becomes a black hole. And matter compresses to a point that is beyond our knowledge of physics. The reason why it's called a black hole is because matter is so dense here, it exerts a huge gravitational pull that not even light can escape. And if you ever to enter into a black hole, you would be stretched out, and your atoms would be stretched out. And one of the interesting ideas of Einstein, which has been proved, that gravity will slow down time, so that if you did enter a black hole, time would stand still for you. And in fact, another part of Einstein's theory of relativity is that as you approach the speed of light, time would slow down for you. Now, this is a black hole, and it's normally black holes, you can't see them, but if they're near a sun, it'll start it'll start absorbing that star and giving off radiation. And this is one of our probably the most greatest living theoretical physicist, Stephen Hawking. He's at Cambridge University, holds the professorship that Isaac Newton held. And what he says is that black holes will radiate, eventually will evaporate. And unfortunately, he has contracted a form of Lou Gehrig's disease and can communicate only through a computer, but his mind is brilliant. This is called the Coil Galaxy, and in the center of this galaxy is a black hole, as probably all galaxies, including ours, have a black hole. This is a diagram of our solar system, and it's, again, somewhat distorted and diagrammatic. But starting from the left, we start from Mercury, Venus, Earth, and Mars in between, and then the huge Jupiter, Saturn, and Uranus, and the far right is Neptune. There used to be Pluto as a planet, but unfortunately it got demoted for a number of reasons, and that's not considered to be part of our solar system. The reason why we know our solar system is 4.6 billion years old is because of meteorites. This is a sliced portion of meteor called the Allende meteorite, and because it landed near Allende, Mexico, and it has been age dated and found to be 4.6 billion years, and it's part of our solar system, so it follows that our solar system is that old. Now here are some images of planets. This is Mercury, and you can see how tiny it is compared to the Sun. And this is Venus. Despite its name, Venus is not a place of paradise. Venus is completely covered by clouds, and it has a dense carbon dioxide atmosphere, and this is a greenhouse effect gone awry. And those clouds you see are made out of sulfuric acid, the same acid that's in your battery, car battery, and the surface of Venus is enough to melt lead. This is a radar image of Venus, and that mound you see in the distance is an extinct volcano. Now, this is a diagram comparing Earth. You can see that little blue dot on the left compared to our Sun. And you can see what a pipsqueak it is. If we could quit fighting over this little speck, we could be a lot better off. This is the moon, and if you ever get binoculars, the greatest time to observe the moon is at half moon, because if you look along that border between dark and light, the cliffs and craters will cast shadows, and you can really see them very well. And you'll notice how cratered the moon is. Our Earth would look just like that, but the fact we have an atmosphere and weathering and erosion that has destroyed most of our craters. And yet there are a few still around. This is the Barringer crater in Winslow, Arizona, and it's named after Mr. Barringer, who looked for what he thought would be the iron nickel that would be in that center of the crater. And pieces of meteorites, iron nickel meteorite, have been found around that crater, but there seems to be a geophysical anomaly suggesting that there might be a large mass in one of the walls of the crater, but no one's investigated that. This is the Manicouagan crater in northern Quebec. If you remember earlier, we saw that in the Aurora Borealis, and right now it's being used as a hydroelectric reservoir, but this is another crater that's recognized on Earth. And this is Apollo 11 coming back from exploring the moon. And this is Mars. Mars is a dead planet, has a very thin carbon dioxide atmosphere, and stretching across that is called the Valles Marineris, and that is 2,500 miles in length. Makes our Grand Canyon look tiny by comparison. And in the upper left-hand corner, you'll see two blots. Well, those are extinct volcanoes, much, much higher than any of our volcanoes here on Earth. And this is one of our explorers on Mars. As far as I know, it's still going. Unfortunately, its solar panels are being covered with dust, so it can only operate about an hour a day. And this is what a photograph from that rover. Mars looks inviting from this diagram, but look, there's no vegetation, and because of the fact that Mars does not have a magnetic field like Earth does, the solar radiation is just pouring down there. Anyone who stepped out there, other from the fact there's no oxygen, would be immediately radiated. The next slide shows Jupiter. And Jupiter is a wannabe sun. It's a huge ball of gas, mostly methane. And if it had been larger, it could have been a star, but it just wasn't big enough. And the other two gas balls, Uranus and Neptune, are similar, but they're blue in color, and I won't go there. Now, this is one of Jupiter's moons, and it's not an old pizza, but this is Io. And the reason why it looks so blotched is because it's very volcanic, active volcanically, and that yellowish color you see is sulfur. Now, Io is a dead moon, but it has heat generated by the fact it's stretched and warped because it's so close to the huge gravity pull of Jupiter, and that heat generated by the stretching provides the heat to provide for volcanic eruptions. And this is arguably one of the most beautiful planets in our solar system, Saturn with its rings, also a gas ball. And surrounding our solar system is the Oort cloud and the Kuiper cloud, from which our comets come from, the ice balls. And you'll see in the top of your picture Pluto's orbit, which really goes canter-wise to the solar orbits of the orbits of the rest of our planets in our solar system, which is one of the reasons why Pluto is not considered to be a planet anymore. Now, all these great pictures come from telescopes, and this is the Keck Observatory in Mauna Kea in Hawaii. And what you want to do is get up high enough so you're out of the distorting effect of our atmosphere. And Mauna Kea is an extinct volcano, and there are mirror telescopes inside. And this is the next slide will show the primary mirror of the Keck telescope. And you can see that it's made of pieces. You couldn't cast a mirror this large in size. It would warp. And by the way, Newton was the one who invented the mirror telescope. This is Arecibo in Puerto Rico. This is a radio telescope. And what they did is they built a dish at the top of a sunken cavern. And this telescope does not move. What it does, it's a radio telescope and observes the universe with the rotation of the Earth. And the next slide shows the Cassini-Huygens propulsion module. And this is part of the satellite that was sent out to Saturn. And it did a flyby by Saturn to observe its rings. And this is the reason why we can get one of these wonderful pictures that are even, in some cases, better than what the Hubble telescope can provide. And of course, we have the space shuttle. Here's one on the launch pad. Next slide shows it taking off. And next one showing further. And these are different space shuttles. And this next photo is an optical image. The space shuttle never flew that close to the sun, but you can see what it looks like relative to that huge star that we depend on, which is our campfire in the universe. If we didn't have that star, we couldn't exist. We completely depend on the light and heat emitted by our sun. This is an artist's representation of a space shuttle docked to the Russian space station Mir, M-I-R, but Mir is no longer in orbit. It fell out of orbit and plummeted into the Pacific Ocean. And this is the International Space Station, which is still orbiting us. And the space shuttle fleet will be retired next year. And this will be replaced by the Soyuz Russian spaceships, not as pretty as the space shuttles, but as you can see, a lot more simple. And this is a astronaut floating by himself in space, a very lonely place to be. And finally, we come to one of our ancestors, Australopithecus africanus, who lived 2 million years ago. And in our evolution, we can, and recently, human ancestors that go back further in time, 4 million years ago, have been discovered. And we can assume that in 2 million years hence, 4 million years hence, we may look like that to our descendants. And so I have some final thoughts to this presentation. 5 million years ago, Quincy was covered by a mild thickness of ice. And in 5 million years hence, the ice will return. If you go to Kincaid Park on Water Street, you'll see that there are polished outcrops, which is evidence of the last visit of our glacial visit. 200 million years ago, the continents came together in a continent called Pangaea, and today we're living in a Goldilocks moment. The continents are separated and they're bathed by oceans moderating in our climate. In 200 million years in the future, the continents will come together again, creating one huge continent. And the center will be a big desert because the center of this huge continent will be away from the ocean. You can think of Alex Springs in the outback of Australia. Now, to escape our destiny, Einstein said that the speed limit of the universe is the speed of light. No matter can go faster than the speed limit of light, which is 186,000 miles per second. That's not enough to escape the universe. There's such a thing called spooky entanglement, which Einstein termed, because one particle can affect a particle at the same instant at a distance. In the universe, we know that there are virtual particles that twinkle in and out of existence. Now, our universe is 13.7 billion years old. It's possible that a civilization could have developed 1 billion years ago. If so, where are the aliens? in order to space travel, to travel in out of the universe, and eventually in 100 million years our universe will no longer exist, we will have to be able to leave. And it could be that the nature of evolution will lead to our destiny by a non-corporeal form. That is, we'll leave our matter existence and become pure thought to be able to travel. It's just an idea, and in the millions of years to come, we no longer have to depend on nature to determine our genetic future. We can determine it ourselves. Thank you.